Okay, so far we have looked into linear regressions, okay, which basically try to fit a line through the data points that we have. Now we're going to look into slightly more complicated functions. So polynomial regressions are a type of linear regressions in which the relationship between the independent variable and the dependent variable, between x and y, is modeled with an nth order polynomial. So what you can see there in the function is that it's still going to depend on a set of parameters, on a set of thetas, but instead of having just one or multiple independent variables, here the variables, the x variables that we have, are based on an nth order polynomial. Okay? So as we vary the degree, the p degree, the degree that we put on the x variable, the fit, in principle, the fit improves and the risk decreases. Okay? So look at the different p-values. If we start just with a p-value of 0, it's just a plain line. We have the fit, as you can see, is terrible. If we start increasing the p-value, the fit, which is a red line, starts improving. It starts, adapting better to the points. And the risk, which is the number that you see in the box, the 55, 16, 0.9, 0.93, 0.70, and 0.23, that's the risk. So what we observe is that, the higher the polynomial, the better the fit. So the better function, we are finding a better function that actually defines the actual shape of the points, the actual relationship between x and y. And as a result, the risk is decreasing because remember the risk or the loss is measuring the difference between the actual value and the value that the function gives us. So, both things are improving. Is this good? Not completely, okay? And we'll see why. Basically, in order to find that fit, similar to the linear regression, we need to find the value of the intercepts and the slopes, so the theta values. But in this case, we also need to find the p-value, okay, which is the nth order for the polynomial. Now, we say that it's unfair to use the risk to find the best p, okay? The reason being why, this is based on overfit. So what happens, and let's go back to this slide, what happens is that actually when we use training data to compute that function that basically adjusts really, really well to the data points, we call it, what might be happening is an overfit. And what an overfit means is that we are adjusting with the training data really well, the function very well to the training data, but what might happen is that when we use the testing data to understand the quality of our model, we might be doing really poorly. Why? Because our model fitted too well to the training data without taking into account that, there might also be errors in the data that we are using. There might be noise in the data points that we are using, okay? So it turns out that, high P implies a risk of overfit. And as I was saying, we have a perfect training, but, predictions are not going to be that good. So what this means is that when we have a model, both, and not only for the polynomial regression, that might also happen with a linear regression, okay? We really want to make sure that the model generalizes to future data. So we really want to make sure that when we, train, we train on a set of training data, and then we test on new data, okay? So the typical approach is to split data into what we call training and cross-validation, okay? Then we use to estimate the theta values, we use the training loss, and to estimate the p-value, we use the cross-validation loss. Okay, so what this means is that we're going to use one data set to compute the theta values, and another data set to compute to estimate the p-value. Okay, so when we are fitting polynomial regressions, it will be critical to differentiate or to divide the training into two sub-training sets, the training and the cross-validation, okay, so that we do not approximate, we do not estimate all features, all theta and p at the same time. So we'll first estimate theta using, the training loss function, and then we'll estimate the p-value using the cross-validation loss. Okay, it's the same philosophy. So what's the difference between the real value and the predicted value? But we're going to do it twice, one for the theta values and another one for the p-values. Why? Because we don't want to generate a model that overfits, that adjusts really really well to the training data, but then predicts poorly, generalizes poorly to future data. So as I was saying, we are looking for the best p-value, and the best p-value is one that it's not gonna underfit, meaning that we are gonna have a lot of or the difference between the actual value and the predicted value is gonna be really really large, so we are underfitting. But we also do not want an overfit. Okay, an overfit happens when the difference during training is really small, but then during testing is huge. If you, for example, ever train a model with training data, and then when you test it, and the training data, it says that the accuracy is really good, and then when you test it, the results are really really poor, that means that you have overfitted your model. Okay. So again, as I was saying, what we just explained, is how different functions that fit polynomial or regression or linear regression models work internally, in any type of machine learning package that we are using in order to fit that model, in order to obtain the parameters that will define that model. And in the case of a polynomial regression, it basically works with the training and the cross-validation datasets. Okay, again, this is not something that you necessarily need to do, but it's something that R, in our case, will be doing internally when we run different packages. And there are other types of regressions like sinusoidal or radial basis function, depending on the function that we use to basically approximate the dependent value based on the independent variables.